Hi, in this video, I'll talk more about series and continue our journey in real analysis. So in the previous video, we've talked about what are convergent series, which are actually sequences that are the partial sums of another from a given sequence. And so there are some properties about convergent series. If let's say A and B are convergent series, then when you add them up term-wise, they will still be convergent series. And their limit will equals to the limit of the series AK plus the limit of the series BK. Also, if for any scalar you multiply it to a convergent series term-wise, then the resulting will also be a convergent series, and it will just be a scalar times the limiting value. And really what we are trying to do is we treat them as sequences and use the properties of convergent sequences. So I'll leave it to you to do the proof, but you can just use this idea because you are now treating them as sequences, which you should. And why I say they're convergent when you must add them term-wise is because convergence occurs term by term. So let's say you got 1, 2, 1, 1, 1 all the way, and then it's 2, 2, 2. Term-wise will result in 3, 3, 3 all the way. And then this means it converges. But let's say now you have 1, 2, 3, 4 all the way, and then the other one is similarly 1, 2, 3, 4. And now you take 1, you add with 3, 2, you add with 2, and then you so on, and then you form an entirely new sequence like 4, 4, 5, 5, 6, 6. And then it will become very hard for you to understand whether it converges now. So you have to know that we have to add it term-wise when we ever add sequences together. And the resulting will result in still convergent series. However, this gives us the idea of coming up with a notion known as absolute convergence. And absolute convergence is not just about the it's more about the nature of the sequence converging compared to what the sequential limit is. So a series is said to be absolutely convergent if the series, so now you have a new series where all the terms here are the positive terms, converges, and these terms are in the real numbers, so it converges in the real numbers. This series can converge in the original field or the original space V, but this absolute convergence will converge in the real numbers. And so if a series is absolutely convergent, then it converges itself. And it really just follows from using the triangle inequality, and then because real numbers is Cauchy complete, this will be using the Cauchy criterion over here. And so if a series has just positive terms, then absolute convergence is the same as convergence. And if AN converges, but AN does not absolutely converge, then we say it's a non-absolutely convergent series. And this is one that shows. So it's possible to be to converge but not converge absolutely. And with that idea now, we can say whenever we say about absolute convergence, we can always talk about normal convergence, but not the other way around. And so it comes to us that why do we care about this? Because it shows that if you know that a sequence is absolutely converging, then you can rearrange the terms and it'll still be converging. So that's what it means so then we don't need to do it term-wise already. But before that, let's just talk about what this term-wise means. It means that if you can have this idea of a rearrangement basically. So you can take this converging series and then you rearrange them in such a fashion. Now you can see the top series will the limit will always be less than 5 over 6, less than or equals to 5 over 6. But the bottom, you can already show that the lim sup will be greater than 5 over 6. So there's no way the bottom will converge to 5 over 6. And so this means that we are unsure whether this rearrangement is convergent or not. But if we know it's absolutely convergent, then any rearrangement will be convergent and to the same sum. And the proof follows quite interestingly, because so now we just take a rearrangement. So the terms are now rearranged in some weird order. And then we say that the partial sums are Sn prime. We know that it converges absolutely. So there will exist a point, a cutoff, such that any 2 points above it from n to m, the series an converges. Or it will be less than epsilon. Now we just need to pick. So what Rudin says, we need to pick a p such that all these terms are within it. So because we know the permutation is a bijective function, we can choose the n such that all these capital N's, 1 to capital N, will be a subset of this from K1 to Kp. So this is like the this will be like the bijection. So you can spread out your bijection far enough so you capture all these 1 over n's. And so when you take Sn prime minus Sn, what you're left with is only the k term, whether it's plus or minus, with k greater or equals to n. So how you visualize this is, you have now this a1 plus a prime 2 plus all the way, and then you're minusing a1 minus a2 minus all the way to minus a capital N, and then you minus a capital N plus 1 minus all the way to a n. Then this is adding all the way to a sigma p, a sigma n. Then because this a sigma n would encompass all these capital N's, this portion will cancel out. And so what and then maybe the first n terms will also cancel out. So what you're left with is a n plus 1 plus all the way to plus a sigma n minus away a n plus 1 minus all the way to minus an. But because it's a bijection, so if you just take like n terms on this side and n terms on this side, then you cancel out equal number of terms on both sides. When you add them up, you're basically just taking the terms, but now it could be just negative of ak. So you just do it as follows, and then because it converges absolutely, doesn't matter whether this is positive or negative, it will still converge. So by the Cauchy criterion, it will hold. This will hold. So Sn minus Sn prime will be less than or equals to epsilon. And because epsilon is arbitrary, this means that Sn will approach Sn prime. And because Sn prime will approach Sn, and because Sn approaches S, Sn prime will have a limit of S. And so Sn prime converges and to the same limit as the original series. And so that really shows us how, if we already know a series is absolutely convergent, then we can just rearrange the terms anyway and will still give us the same sum. You can read more about this rearrangement, but I won't delve too much into the details because it's really, once you get the idea, then you can rearrange them. And writing it out rigorously is usually the hardest part about this proof. And so let's end this video with a nice simple exercise to get us familiarized with absolute convergence and normal convergence. is that if we can prove that a sequence converges normally, then it implies that the sequence, the partial sums, the modulus of the partial sums will also be convergent. So you can just take, they're given an epsilon, then you can have a cutoff such as Sn minus S is less than epsilon. And then you know that by the triangle inequality, Sn the absolute value of Sn minus the absolute value of S will be less than or Sn minus S. Strictly less than. So this will be less than epsilon. And so this converges to S. And we're done. So I hope the proof is fairly simple. However, the converse fails because if you take An to be minus 1 power n or Sn to be minus 1 power n, then Sn will converge because it's the constant value. The absolute value will converge because it's the constant value 1. But minus 1 power n does not converge. And you should be able to show why from our previous videos. And I'll leave it to you. And so we are done. And this really recaps convergence and absolute convergence. And so in the next video, we'll continue more about the topic about series first before we actually do more real analysis on functions. And so that's all for this video. I hope you've enjoyed it and I'll catch you in the next one. Bye.